Today we are going to learn about the molecular orbital theory. So, molecular orbital theory, what does it mean? That means we are familiar with the atomic orbital. You are familiar with the atomic electronic configuration. So, when we have some molecules, in that case, we also have some electrons, because all the atoms combine to form a molecule. Therefore, if the atoms has some electron, the molecules also have. Therefore, how they combine when two or more than two atoms combine together? So the electrons will also combine, or the orbitals will have some sharing, overlap, or just different types of orientation. So how the electrons or how the orbitals in a molecule combine to form the molecules, we will discuss this, and in this chapter we will learn the molecular orbital theory. So first we would like to see atomic and molecular orbital. We will learn about the atomic and molecular orbital. What is atomic orbital? Where the electrons are available or found. That means the area or region where the electrons can be mostly found. So if we consider like this way, we will have a lot of, okay, for hydrogen molecule, we may have some, the electrons are found this pattern. That means the possibility of having electron in hydrogen atom just like this way. If you can consider like as a football or some ball or a sphere, in that case the where the electrons can reside or where the availability of electrons for atom. So atomic orbitals depict where electrons are most likely to be found in it. Similarly, when we have a molecule, there is some possibility where we can find the electrons more and where electrons can be found less. So similarly, molecular orbitals tells where to find electrons in the molecule. That means you may have some molecule where the possibility of having electrons is very high, and some of the place where the possibility is very low. So we will be able to learn from the molecular orbital theory where the electrons will be or where will not. Okay. Electron configuration of molecule or a special distribution of energy. So all of you are familiar with the electronic configuration of atom. But now we will try to learn the little bit where the electrons can reside or where the electrons can be in a molecule also. Now, if you have two different types of atoms, both of them have some electrons. Now, if you have two different atoms with different bonding combination, the wave function. Wave function, this is psi. That means, what is the wave function?
The electron which behaves like wave, we have to do a nature of movement. So for that we use wave.
Actually, just if I represent like this way, the wave function is represented where the electrons are found. That means how the electrons behave. That means just if you write down any equation or any function, f of x equal x square, or you can write down y equal x square, something like this. So f of x equal x square, this is a function. So when you change the value of x, the function or y changes the value. So that is x. So that means this is x is a function of x square, or y is a function of x square. So this is a function. This is also another function. So depending on the value of the psi, the possibility of having electron can vary or change. So actually the psi is the function where by how we can represent the orientation or the availability of electron. Right? So when two atomic orbitals with wave function psi a and psi b are combined, the resultant orbitals are okay. One thing, if you have two different orbitals, maybe we can consider this is one orbital and this is another orbital. So if you have two different orbitals, now this is atomic orbital, this is one atomic, this is another atomic. Now when these two orbitals combine each other, the summation, the resultant or product, actually product is not always the multiplication. For chemical reaction, how do we write down? A plus B getting some product C. Is it? So that is can be considered as this is product, this is reactant. So you always don't need to think about A multiplied by B equal product. So sometimes we can say this is also a product. This. So the resultant of these two atomic orbitals, that means when these two atomic orbitals combine each other, they can have the resultant. That means actually I will write down, if we have the atomic orbitals like A and B, in that case the resultant can be plus minus the summation or resultant wave function of these two orbitals can be the sum of, or that means this is the resultant either plus or minus of these two orbitals. So if you sum both the orbitals, then you will get that these two orbitals combined to have the energy even lower, and we consider that as bonding orbital. So that means if these two orbitals overlap in that way, that means these two, the wave function just sum up. So if you have two wave functions of psi A and psi B, and then if you have the resultant by summation just plus, that means these two orbitals, then if it comes close, in that case we can have, maybe you can write down this one, this is coming like this way. So what will be the resultant? This is our resultant. So this is one part, this is psi A, this is psi B. So sum of these two orbitals, if we have this types of combination, that means the summation of two wave functions or sum of two wave functions, in that case we can have the bonding orbitals. And if you have these two orbitals minus, so if you want to have this minus like this way, two orbitals, then minus each other, that means we will subtract this part, will subtract, so we will not have this part. So how we can write down that part? That should be this phase. That means in this region you will not have any. So I should write down maybe later. That means the possibility of having electron in this area will be 0. That means there is no electron. So here we have the possibility, that means in this region, what we have drawn here, this is common for both of them, and we can have this area. That means this area have the possibility of having electron even more, and here this area subtracted. So this area have the electron. We call this area is node or nodal plane, where the possibility of having electron is almost zero. That is considered as node or nodal plane. Nodal plane. Okay. So when two atomic orbitals with wave function psi a and psi b are combined, the resultant orbitals are psi equal Ca psi a plus Cb psi b. That can be bonding combination. And this Ca and Cb, that are just some components or constants, arbitrary constants. So when we are having this structure combination, this area, just how much it has overlapped, the Ca and Cb will be dependent on how much it becomes the overlap or how much it overlaps. So even for this one also, Ca and Cb, it will depend if the orbitals overlap little bit more. In that case, this area will go little bit higher. So that means subtraction will be even larger. So that depending on how much the overlap comes, the value of C and Cb, the coefficients or constants will be determined. Yes, arbitrary constants. So there is no specific value. The resulting molecular orbital can also be non-bonding. Okay, that is another thing. That means if you have water molecule, so we know that water molecule has the hydrogen potentially, like this structure and this structure, this structure. So this has some orbital. That means if we write down, this comes from the 2p orbital, is it? And this is 1s, this is 1s, and here, if these two orbitals are not bonding together to make the water molecule, therefore we can consider these electrons as non-bonding electrons. Here, this electron is bonded with hydrogen. This is so here later we will show the structure for water molecule, how we can represent the structure or how we can share the electrons. But here you can see easily these two electrons are not participating in the bond. Therefore, we can consider these two pairs as non-bonding electrons. Simplest molecule, all of you are familiar with hydrogen or H2 molecule. Now, as already I have shown here, that this is isolated hydrogen atoms. This is hydrogen atom. So this is another hydrogen atom. Already what I have shown here. So these are the energy. Just we can show one scale. So when these two isolated hydrogen atoms, that means two 1s orbital, this is 1s, this is another 1s. So when they combine, they will form what I have shown here, like this. So this is the bonding, and that is the node what I have shown that. So this region we do not have electrons. So here you can see some places. Molecular orbital, bonding molecular orbital, sigma 1s. Now we are familiar with the word sigma and pi. Sigma bond, pi bond. What does it mean, sigma bond and pi bond? Yeah, that is one way. But we have some special representation of sigma and pi. If you have some bond, so bonds are formed by sharing of electrons in covalent bond. So if the electrons are the orbitals, if the orbitals are shared face to face. In that case, we can consider that would be sigma bond. And if you have the orbitals share side by side, in that case, there would be pi bond. We will see. Maybe I can show you just very quickly. If you have a p orbital, you are familiar with the structure of p orbital like this. This is the p orbital. So maybe we can consider this is Pg. Because we know p orbital has three different types: px, py, pg. So pg, px, py, like this. So if you have another p orbital like this, in that case, there is possibility. Just I can show one p orbital. This is one. So, sorry. Okay. Any question? Okay. So, if you have the orbital like this way, now, if you have another p orbital, in that case, you can have the bond that can possible. This is from one atom. This may be, this is carbon and this is another carbon. That is possible. That means these two p orbitals are overlapping face to face or head to head. We can consider. So in that case, here we can have a sigma bond. Similarly, we can have like this way. Same thing. No, not this is not side by side. Side by side, I will draw another way. So this is face to face. This is face to face or head to head. And if you have some orbital, this is one carbon, this is another carbon. Already I have drawn here px, py, pg. Let us consider this is py. This is another py. Now, if these two carbon come close, in that case, what can happen? So this is py orbital, this py orbital and this py orbital can overlap. So in that case, you will have a configuration like this. So here, this is two orbitals. It can come close together like this. So here, if this carbon come close together, so this is the side by side overlap. So here we can have pi bond.
Also, sometimes for valence bonds, we have SPG. But when it comes to a molecular orbital, we have this side and pi.
Yeah. For any molecule, for covalent bond, if you want to explain, just we will have different types of theory. So how we can explain how the atomic orbitals combine, and then some of the theories may have difficulties, and then we have to go for other theory so that we can also explain the property. So one by one we'll see how we can explain, or what are the orbitals, or what are the theories we can use how to explain. So here what I'm going to show here, as two orbitals. One thing very interesting, when you have any one s orbital or s orbital, always you will have the sigma bond. Why? Maybe all of you can understand, but you cannot explain. Is it? Because if you have some orbital, one orbital like this one, and you have another s orbital, 1s, 2s, 3s, 4s, whatever. So in that case, s orbital shape is like this. Is it?
Yes.
Spherical.
Yes.
Spherical.
Yes.
So in what you have wanted to say, s orbital,
No, I think it's not okay.
then how do you think? S orbital should be like this? No. No.
In underway, we have this sum. We have. So if it's filled, we can't go for overlapping. But if it's unfilled, means one screen, then we can go for overlapping, right?
Until, yeah. So
That way also one sigma.
no, just simply, this is 1s. It can have 1s too. That is filled. But if you have the s orbital, then you will have the sigma bond. Why? The shape of the s orbital is spherical. That means every side is same. Every side is same. But in case of p orbital, what I have drawn, if another p comes here, you will have side by side. If the p comes here, you will have head to head or face to face, but not side to side. So, but in case of s, if you bring this s to here, if you rotate this side, that also comes to the face. So, if you have the s orbital, you will always have the sigma bond. Whatever the other component, so always you will have the sigma bond in case of s orbital. So, what I was going to discuss about this, in case of what hydrogen molecule, this is the 1s orbital, this is another 1s orbital. So, when already we have mentioned in the previous slide that the resultant, if the resultant is the summation of two atomic orbitals, then we will have the bonding orbital. And what does it mean, the bonding orbital? The energy of the two atomic orbitals will be lowered. Can you see? This axis is the energy. So this is the energy of the one atom. This is another. Both are similar. Therefore, the energy of two hydrogen atoms will be same. Okay. Now, when these two isolated hydrogen atom combine, that means two 1s orbital combine together to form hydrogen molecule. In that case, energetically it goes down.
Why?
Because when this hydrogen and this hydrogen combine each other, they have the stability compared, if you consider for the helium, because this hydrogen need one electron to get the configuration for helium. So this hydrogen also need one electron, but when they come close together, they form a bond so that they become more stable and they get the configuration of helium. So it becomes stable. So how they become stable? By releasing some energy. So they release some energy so that the energy of this hydrogen molecule becomes less compared to the atom. Now, then how it equivalence? There are some these electrons, when they have, we have mentioned that they have the possibility to get the, this is type A, this is type B. So the resultant would be plus minus of the two orbitals, two atomic orbitals. So when these two complete sign plus, then we are getting the bonding orbital. When we are having the minus, then we are having the anti-bonding orbital, and the energy of anti-bonding orbital is higher because as much energy we can see, that means from here, when the energy of these two atomic orbitals, how much is lowered, it will get the as exactly same mass, same amount. That means So this is the analysis for the anti-bonding. So most of the time you will get the electrons here and here we do not have. But in case of another atom, we will see some of the electrons go to the anti-bonding orbital, and the characteristics and the magnetic properties we can also explain the how by from the molecular orbital theory different way. So here you can see, if you consider the hydrogen oneness, it has one electron and this has another electron. So when this electron combine to another electron, so actually here you can see that two electrons are coming, so they form, and this is one electron, this is another electron, this is, so here we do not have any electron. But if you have any atom having the, we can consider this is not hydrogen, we can consider another one, helium. In that case, we have this. Then you will have some electron. This is one orbital, this is the bonding orbital, this is the anti-bonding orbital. So first we will fill the orbital minimum energy orbital, and then if you have another electron or more electron, then it will have into the higher energy orbital. So we have 3 electrons total, 1 and 2, 3 electrons. So first this one filled because only 2 orbitals with opposite spins can have into the one orbital, and then as we have 3 atomic orbitals, so one will be so by this way. So now we will see the bond order. That means how much strong the bond will be. If you have some molecule like this way, bond order is calculated by the formula equal half multiplied by the number of bonding electrons, bonding electrons minus number of anti-bonding electrons, B anti-bonding. I should write the same way. B anti-bonding. B and P. So number of bonding and number of anti-bonding. So here you can see, in case of hydrogen molecule, or if you write down now, if we consider in case of helium, here helium, another helium. In that case, we will have another electron in the top. Okay. Now let us calculate the bond order for helium 2 molecule. This is the formula: half into bonding orbital minus anti-bonding orbital. So half, 2 minus 2, that will be 0. Therefore, you can consider that the helium molecule do not exist. You always know that helium cannot form molecule. Is it? Helium is a inert gas. Is it sure? So now we can see that the bond order of helium molecule is 0. But in case of hydrogen, in that case we have only 1 electron here, 1 electron here, and there no electrons. Is it? Then what would be half into 2 minus 0? 1.
So can you explain that diagram in terms of relaxation?
Sure. Why not? Later we can go. First, here you can see that for helium, the bond order is 0. Therefore, you can easily understand that He2, this molecule does not exist. And in case of hydrogen, the bond order is 1. Therefore, the hydrogen molecule can be H2. So from this point of view, I would say if any molecule has the bond order greater than 0, that molecule can be possible or exist. And if the bond order is 0 or negative, in that case, the molecule do not exist. Okay. Now you have mentioned for oxygen. Maybe I have atomic antibonding. What is the configuration for oxygen? Just 1s2, 2s2, 2p4. Is it total 8 electrons? Okay. So now you want to have the molecular diagram of oxygen molecule. That means 2 oxygen atoms. Is it? 2 oxygen atoms. Let us consider this is one oxygen and this is another oxygen. Maybe write down first here and here. So how many electrons you have? We do not need to consider about the first shell because first shell they do not combine for the bonding. That means inner shell. For any molecule to form or any bond formation, we just need to consider for the outermost shell. Is it? Because inner shell do not have any possibility to have the so outermost shell or outermost electron will be participating. So let us consider only second shell. So in the second shell, we have how many orbitals? 2s and 2p. 2s2 and 2p4. Okay. So 6. So let us have maybe write down. This is our energy. So that is energy. And what is the energy of 2p and 2s? The energy of 2s is higher or 2p is higher? 2p. Yes. Yeah. 2s and 2p. Just you can calculate with this formula. Sorry, what I mentioned? N plus L, is it? The formula of N plus L. So for 2s and 2p, so value of N is 2 and S is 0, and for 2p, 2 plus 1. So energy of 2p is higher. So we can write down that this is our 2s. So we have 2 electrons here, 2s2, and for 2p, so this is 2s, this is 2p4. Is it? For one oxygen atom. Okay. For another oxygen atom, that would be exactly same. Maybe write down in another side. That is, this is 2s. We have 2s2 electron, and this is our 2p and this is ps. For the 2 oxygen atom, so we can represent that like this way. Just oxygen atom, and this is another oxygen atom. Okay. Now this 2s and 2s, they will have, as already I have mentioned, in case of helium, that is exactly 2s2 and 2s2, is it? That means, let us have like this way. Maybe I can draw it below. That can be even easier. So 2 electron. Now you will have some bonding electron, bonding orbital, and this is non-bonding orbital. So we can have, so here 2 electron from here, 1 electron from here, 1 electron. It will come to combine to make the. This is the bonding electron for 2s. Here we will have, as already we have shown, the helium. So we will have, okay. So 1s2, this is 2s2, this is 2s2, this is also 2s2. So this is our bonding orbital, this is anti-bonding orbital, sigma, sigma star. Now, when it comes for the 2p, as many as we have 3 atomic orbital, we will have these 3 atomic orbitals, so total 6 atomic orbitals. We will have 6 bonding orbitals. That means among them 3 will be bonding and 3 will be non-anti-bonding. So for bonding, we will have, maybe I draw this way. So that's fine. We have so in the up it should be 1. So 2p orbital will have first take 1 electron from here to fill all the bonding orbitals. So from here 1 going, and from here 1 coming here. Then you have 1 electron here, and you can give here, and so this 2 is completed. Then you have 4 more electrons. These 4 more electrons, first it will 1 come here, from here, and then from 1 here. Okay, and you have this one done, this one done. You have 2 more electrons. We are giving the energy from the first. We fill the minimum energy orbital, then going to up like this way. Now you can calculate the bond order for this molecule. Number of bonding electrons 2. This is our bonding, and this is 6 plus 2, 8. So formula is half into 8 minus 2 and 2, 4. Then let's have the bond order 2. Half into 8 minus 4. So bond order for oxygen molecule is 2. That means in case of hydrogen, we have found bond order is 1. Therefore, we have mentioned that the hydrogen molecule exists. Bond order for helium molecule we found that is 0. Therefore, helium do not exist. Oxygen bond order 2 that exists. Now, one very interesting property, as already I have drawn this one. I will explain from here that if a molecule is paramagnetic or diamagnetic, we can explain using these types of molecular orbital diagram. How? If the molecular orbital have the unpaired electron, in that case, the molecule will be paramagnetic. If the molecule has unpaired electron, this is unpaired, is it?
Yes.
Therefore, the oxygen molecule is paramagnetic. So, any molecule having the unpaired electron, then we will consider that molecule as paramagnetic. So, what is paramagnetic and diamagnetic?
Paramagnetic is something that will get affected to magnetic, but the diamagnetic is little of it.
Yes, we are right. So, paramagnetic, as she mentioned, that something. Let us consider the iron can be attracted by some magnet. All of you are familiar with this. So, the iron is a paramagnetic substance. That means oxygen, from this character or this property, we can consider that oxygen also a paramagnetic substance. You can attract, the oxygen can be attracted by magnet. So, that is paramagnetic, and diamagnetic, something which do not attract, then it repel. So, the diamagnetic which do not attract the magnet. So, oxygen is paramagnetic. Already in the same slide, I didn't say. H2. Yeah, H2 you can say no. Diamagnetic. Yeah, it do not have no unpaired electron. So H2 no unpaired electron, therefore it is diamagnetic. So any molecule, if you have the unpaired electron in the molecular orbital, in that case you can consider that molecule is paramagnetic. If no unpaired electron, then it should be diamagnetic. So what we had several examples. Simplest molecule we wanted to show, and then we have gone from here. Already I have discussed this thing, but not in this format. Why do you get these types of wave functions, or when we combine these wave functions, two wave functions or two orbitals, then why you get the summation like this way, and that is subtraction. That means if you have the wave function combined for sigma 1s, this is a wave function, this is another wave function. When these two are added, that means this is one function, this is one function. So when these two are added, then it overlaps only what I have shown for two circle or two sphere. Thus they are representing in another way. So some part of this orbital and some part of this orbital will overlap. Therefore, they will have this common part, common portion. Therefore, we can consider this is the summation or sum of the combination of two orbitals for 1s. Alternately, subtract. If you have this is positive, this is negative. So we are giving the opposite phase. That means this is in positive phase, this is also positive. So when these two positive numbers sum up, then you get another very big number. When two numbers with opposite sign are sum up, this is also sum up, opposite sign. So when these two numbers or two orbitals with opposite direction or opposite sign, these two are sum up, then what happens? This part, and this part cancel out. Is it? This part and this part cancel out. So what remains? Just only this part and this part. So we are having these two parts are cancel out. So this portion will have nothing. This portion will have nothing. So we can have this area as node or nodal plane. Okay. Bonding, anti-bonding, non-bonding orbitals. So bonding orbital interaction in phase. That means just if the orbital. In same phase, if the bonding orbitals overlap in same phase, in that case we can have the bonding interaction in phase constructive or symmetric. What we have shown here, symmetric. This is same direction, same phase. So these are similar or symmetric. So they can have bonding interaction is in phase, constructive or symmetric. The resulting orbitals has lower energy already, as we have shown that. Why it becomes lower energy? Because it becomes more stable. So to become more stable, it releases some energy. Therefore, the energy of the bonding orbital decreases, while the bonding energy or the energy of the anti-bonding electron or orbital is higher, because actually they repel each other. Because as already have shown that they are in opposite sign or opposite phase, so just they do not attract at all, even they repel each other. Okay, anti-bonding, the destructive, asymmetric or out of phase interaction. So this one phase, this is another phase. So this is our equilibrium position. So these two are in opposite phase. So when you want to sum up these two orbitals, then this portion and this portion cancel out, then remaining only this part and this part. Okay. And non-bonding, lack of interaction or compatible symmetry. Therefore, if any atom, let us consider for a molecule, not for atom. If a molecule containing electron which do not participate in the chemical bond or any types of bond, inert gas, they do not participate. For inert gas, we have lot of electrons. None of them participate in the bond. But when we compare, we discuss about the non-bonding electrons, just some of the electrons are participating in the bond and some of them are not. As already we have mentioned for water. So two electrons are sharing with hydrogen. So they are forming the hydrogen bond, the covalent bond, and another two electrons, they do not, 2 to 4 electrons, they do not participate at all. Therefore, that 4 electrons are non-bonding electrons. Okay, so same energy as atomic orbitals, that is the for non-bonding electrons, because they do not participate in the bond, therefore their energy also do not change. So for the bonding electron, we have seen that the energy is lower. For anti-bonding electrons, the energy is higher, and for non-bonding, exactly the same. Okay. Bonding molecular orbital, atomic orbital, pz, pi, 2 nodes, not this. Anti-bonding orbital energy, as already we have mentioned that the anti-bonding energy or anti-bonding orbital energy is higher compared to the atomic orbital, and definitely higher compared to the bonding orbital also, because already we have mentioned that the bonding orbital energy lowered quite a lot compared to the atomic orbitals, because it becomes more stable. The amount of energy lowering due to bonding molecular orbital formation is smaller than the energy raised for formation of anti-bonding orbital. What does it mean? That is little bit as already shown here. Here I have mentioned that one word, that I have mentioned that how much energy is lowered, exactly that is same. Actually, not exactly. Not exactly. That means energetically, if sometimes you may have some electron here also. In that case, that means the overlap still we have some possibility of having electrons. Is it? So, in this region we do not have. That means in the node or nodal plane we do not have electron. In that case, if we didn't have anything, in that case we would consider the energy for this portion what is going down and this portion what is going up, that should be exactly equal. But in reality, it lowers little bit high and it goes little bit up. So maybe this one, if we with the value, this is 200, this is 180, something like this. So energy of this, that means energy raised by the, so what we have mentioned that the amount of energy lowering due to bonding molecular orbital formation is smaller than the energy raised for formation of the anti-bonding orbital. Sigma and pi interaction already I have mentioned. That means sigma means the orbital when they are formed just face to face or head to head. Here you can see two s orbitals. These two s orbital can have any types of orientation. If you have two football, you can bring just any orientation. Otherwise, it will be in phase or in the face to face. Therefore, when any s orbital is there, then there you will have the sigma bond. Or then this is one p orbital. We can have for any s. So P Z, then SP, SPN. So later we will go for the hybridization, SP3, SP2, or whatever. So if you have s orbital and p orbital, and so just as already I have mentioned, for if the orbitals are overlapped side by side, in that case we can have the pi orbital. Okay, so sorry, pi bonding. Pi bonding orbitals are symmetric with respect to the joining axis. No phase change due to rotation along the axis. No nodal plane for bonding as sigma interaction. Anti-bonding sigma has a nodal plane perpendicular to the joining axis. So also does not change symmetry by rotation along axis. Okay, that you need to understand. For this one or any orbital, so the orbitals are symmetric with respect to the joining axis. What does it mean? If you have this is s orbital, so this is our joining axis. So symmetric. If you consider just one axis, maybe remove this one. So this portion and this portion symmetric. Again, if you consider for this way the axis, this portion symmetric. Similarly, for p orbital, if you consider this is our p orbital, you can consider axis like this way or like this way. So if you consider the orbital, this is our axis. So this side and this side symmetric, this side symmetric. So even if you consider from this way, this is one axis, this side and this side symmetric. So the orbitals are symmetric with respect to the joining axis. No phase change due to rotation along the axis. So if the orbital changes, that means if it rotates, let us consider this side positive this side is negative. So if this orbital rotates, in that case, what is mentioned? No phase change due to rotation along the axis. So in that case, just it will not change the phase. That means it can go same thing again, or even if it rotates along this way, just it rotating like this way. Same thing, this positive remain same. So the phase change when it changes the when it's rotated along the axis. No nodal plane for bonding SS sigma interaction. This here it has no nodal plane because already we have shown here this is our SS orbital overlap. Therefore, there is no nodal plane for bonding, but for anti-bonding we will have one. Anti-bonding SS sigma has a nodal plane, sigma 1. This is here. This is our anti-bonding. This one. So you can see this is anti-bonding. Okay. So for anti-bonding SS orbital, we will have one nodal plane, and also does not change symmetry by rotation along axis. Already as we have told, just if you change the along axis, this is our axis. Rotate this side positive, this side negative. Let us consider. So when it rotates along this way, it do not change the sign. Pi interaction. This is one p orbital, this is another p orbital. When these two orbitals combine, they can have the possibility to these two orbitals can share. So if they are in same phase, these are not in the same phase because here you can see the color, this color. That means they are in opposite phase. But these two, they are in the same phase. Therefore, if they come close together, therefore these two orbitals can overlap. So there you can see this portion has the possibility of overlap. That means that these electrons just add up. This add up, so they are making the bond, and these two are in opposite phase. So each other cancel out, and then this portion will be empty. There will be nodal plane. So in that case, orbitals are asymmetric with respect to the joining axis. So this is the joining axis. This is the joining axis. So here you can have anti-bonding is also asymmetric, changes phase. There are one nodal plane for bonding, and anti-bonding it should be more than one. Should be. So for bonding, you will have there is one nodal plane for bonding, and for on anti-bonding you will have more than one.
So when they are bonding, they will have one nodal plane.
In case of pi bond,
In case of pi.
but not for sigma, because for s orbital polar symmetric, so there is no nodal plane. But as for p orbital or pi, because this pi orbital, these p orbitals are asymmetric with respect to the joining axis. So a phase change due to the rotation along the axis. There is one nodal plane for bonding PP on interaction. Anti-bonding pi is also asymmetric, changes phase when rotated along axis. One more nodal plane. So for bonding, that means for pi bonding, you will have one nodal plane. For anti-bonding, you will have two. Okay. Now this is the molecular orbital theory. What we are going to learn, number of molecular orbitals that would be exactly equal to the number of atomic orbitals, as already I have mentioned in case of two different here. For there we had 3 atomic orbitals. This is 1 atomic orbitals. 4 atomic orbitals for 1 oxygen. Here we had another 4 atomic orbitals. So in case of bonding orbitals, So molecular orbital, that would be exactly same number of molecular orbitals. So 4 plus 4, 8. So let us count 1, 2, 3, 4, 5, 6, 7, 8. So number of molecular orbitals equal number of atomic orbitals combined. How many atomic orbitals are combined? That would be exactly equal to the number of molecular orbitals. When two atomic orbitals combine, one molecular orbital is bonding with lower energy and the other anti-bonding with higher energy. So when two atomic orbitals combine, they will form one for bonding, another for non-bonding. Electron configuration in molecular orbitals follows the same rules as atomic electron configuration, because you have learned about the Hund's rule, Pauli's exclusion principle. That means later will show, that is electrons enter lowest energy molecular orbital first. That means in case of atomic orbital theory, you have learned that the energy, electron fill the minimum energy shell first, then goes up. That means 1s2, then 2s2, then 2p3, sorry 2p6, and then like this way. So it fills the first atomic orbital first, and then it goes up. Similarly, as already I have shown, when I have drawn, first I have given the electron to this orbital, because energetically this is lower, this is higher, this is even higher. So first I have given the electron to this bonding orbital, then I have given to the anti-bonding, then I have given this orbital, because energetically these are lower compared to this. So even that is highest, that means the top one, that is the highest. So the exactly we are following the rule how the atomic orbitals are filled, because as already mentioned, an electron will fill first with the minimum energy orbital. Okay, according to Pauli's exclusion principle, maximum 2 electrons can go to a molecular orbital. As already I have shown that I have given only 2 electrons in one orbital, not more than 2, maximum 2. It can have 1, because already I have shown here 1. So I have given 1, then why 1, not like this? You know why I have given 2 electrons in 2 orbitals? Yes, if you have the orbital with same energy, then it becomes when you fill half fill. That means in the what is the according to Hund's rule, electrons singly occupy degenerate orbitals before pairing up. That is the Hund's rule, as already mentioned here. So if you have 2 electrons in 2 different orbitals, energetically it becomes stable, more stable compared to, as already we have write down this way. If you write down this way, the energy is even higher compared to if we write down 1, 1. So that is the most stable configuration compared to the if we have 2 electrons in the same orbital. But if you have more electrons, then we do not have any other way. In that case, we must need to give the electron to the orbital. That means, according to Hund's rule, electrons singly occupy degenerate orbital. Degenerate means, what is the meaning of degenerate? Same energized, having the same energy, degenerate. Okay, having same energy. So these two orbitals are same. Both of them are exactly same shape, same size, and same energy. Therefore, they are called degenerate. So when you have 2 electrons with the possibility, they will have 2 electrons in the 2 orbitals before going to pair up. Then a stable species has more bonding electrons than anti-bonding. So as already we have seen for the hydrogen molecule or helium molecule or oxygen molecule. That means if you have the more bonding electrons compared to anti-bonding electrons, then you can consider that the molecule will be more stable. Therefore, the bond order is high. Okay. So here is the bond order. The bond order equal number of electrons in bonding orbitals minus number of electrons in anti-bonding orbitals divided by 2. And we have given yes already happened. So you know how to calculate the bond order. Then we can confirm that which molecule exists and which molecule do not exist. That means if the bond order is less than 0 or if the bond order is greater than 0, then the molecule exists. If the bond order is 0 or less than 0, then it do not exist. Here we have several examples and we can calculate the bond order for different molecules. We have I think all of you are familiar with this. Now you can explain. This is hydrogen. This is hydrogen plus. What does it mean? Hydrogen plus? It do not have electron. Empty. Now already it has released the electron. Just only empty orbital. H plus, that means it has no electron. You can see. Yeah. This is for hydrogen atom. Atomic oxygen, sorry, atomic orbital. This is atomic orbital, hydrogen. It has no electron, but it has the shell orbital, empty orbital. So in case of hydrogen, it has only one electron. So when this H and H plus, they are combining, they are forming the bond. In that case, you can have only one electron. So they are forming this bond. So by this way, you can have the H2 plus ion. That means H2 plus ion, because this hydrogen ion do not have electron. Therefore, we can have in the anti-bonding orbital, it has no electron because first we need to fill the minimum energy orbital. So here we have only one electron. Therefore, we can have only one electron here, bonding electron, anti-bonding electron, 0. So you can calculate the bond order. 1 minus 0 divided by 2, 0.5. Okay, 0.5. In that case, that is also possible. Helium plus. So helium, how many electrons? 2. Helium plus 1 electron. 2 electron will go to the bonding. 1 will be anti-bonding. So already we have mentioned how many bonding orbitals we will have, exactly how much atomic orbital we have. We have one atomic orbital, one atomic orbital. So we will have 2 bonding orbitals also. Bonding molecular orbital, atomic orbital, this is the molecular orbital. So we will have 2 molecular orbitals. This is one, this is another one. Among them, half will be bonding, half will be anti-bonding. As many as atomic orbitals you have. As already have shown here, we have 4 atomic orbitals, 4 atomic orbitals, 8 atomic orbitals, and we will have 8 molecular orbitals. Among 8, you will have 4 bonding orbitals and 4 anti-bonding orbitals. Exactly same. So, and the bonding orbital will have lower energy, anti-bonding will have higher energy. So here we can have first fill up 2 electrons in this orbital. So we have another 1 electron. That electron will jump to the other. So we have 2 electrons bonding, 1 electron anti-bonding. Then we can calculate the bond order. Just 2 minus 1, 1 divided by 2, 0.5. That is also. Is it? So I have helium 2 plus bond order is 1 by 2. Okay. Hydrogen molecule already calculated. No, now we are not doing. Helium already calculated. So helium has bond order 0. Not observed. You can we do not have. So bond energy. One thing. This is the bond energy. What does it mean, the bond energy? Maybe in last class I have mentioned about the bond energy. Yeah, yes, just the energy released. That means the energy released when bond is formed. One bond is formed. But in another way, you can also represent, or you can also tell that the energy required to break the bond. That is the most common one. You always use, but actually we want to form the bond. So that is the bond energy. How much energy is released when one bond is formed? But in if you represent the value, or if you tell the value, that would be exactly the same. How much energy is required to break the bond? So that is same thing. So H2 plus, we are having the bond order half. Now you can see that the bond energy is 269 kilojoules per mole. That means the bond order is 0.5. That means the bond is little bit weak. Is it? Therefore, the bond energy is 269 kilojoules. As the bond order increases, then the bond energy almost double. Is it? Therefore, you can consider similarly bond energy is half. So bond energy even low. So as you can consider as the bond order increases, the value of bond order increases, the bond energy also increase, and the bond length. Yes. Why? And no, explain, no problem. You can say just you are thinking, but you cannot explain. Try to explain. You need bond energy and bond length, that is oppositely related. Then how we can consider that the bond energy, if you have, let us consider two substances. If they have more attraction, they will come close. That is the way. That means this is the high bond energy. Is it? Therefore, the bond length will be, you can see, 74. This is the bond length. Bond energy is small. So lower. Bond energy is lower, therefore, they have less interaction, or the attraction between the atoms is less. Therefore, the bond order is
having best friend and common friends.
yes.
Very close.
Close friends can sit close together, and those friends who are yes. Yeah. That means you are not a good friend of all of them. You are sitting very far away from everyone. Really? And then this has no attraction. Therefore, we could not calculate this. And how far they are, we do not know exactly. Therefore, the bond length is very large. So even actually there is no bond. So how we can consider that is a bond length? So there is no real bond. So we want to complete it. Orbital diagram, the atomic molecule of second period. Same thing. Just yeah. Yes. Okay.